So the period of a function is going to affect, quote unquote, how wide this graph is going to be. We notice how the amplitude affects how tall it is, and the period is going to affect essentially how wide it is. So it's going to be the duration of the wave before it repeats. So in other words, looking at this blue graph right here, here's one wavelength, or one period, I should say, of this graph, and it ends right here for the cosine, and then it's going to go ahead and repeat again, and then do its thing, and then repeat again. And so each of these is a wavelength, and in both of these cases, this blue one has a wavelength of 2 pi, 2 pi, 2 pi. It's consistent 2 pi for this blue graph. The red graph, on the other hand, has actually a period of 4 pi. And it's interesting to note this number, right? So here I have a 1/2, and it seems that if I have a fraction, it actually ends up doubling the period in this case. So the fraction has something to do with making the period longer or wider. If we compare the equations, we notice that for the blue equation, the blue graph, we have cosine x, which if you want, you can put a 1 right here to let you know that this is a 1. And then we notice that the red graph has a 1/2. So again, we note that fractions where the denominator is larger than the numerator, right? When the bottom number is bigger than the top number, we're going to end up getting this effect where the graph is spread out or wider. But in either case, look at part C. We know that the period was 2 pi, right? It started here at 0, and then it went all the way to 2 pi. The amplitude was 1. For the red graph, the period was a full 4 pi, but the amplitude was still 1. So you note that the period does not affect the amplitude. The amplitude is affected by that A coefficient that we talked about previously, and that's responsible for the up and down expansion of the graph. What we're proposing here is that the period, the B value, is responsible for the left and right expansion of the graph. So the general form for our sinusoidal functions up to this point is going to be as follows. We have a times sine bx, and we have a times cosine b of x. And that b is what's responsible for the period. The b is not the period. The b is not the period. But it's used to figure out the period. So the period is found by this little mini equation, 2 pi over b. As an example from the red graph, right, that b value was 1/2. So if I go ahead and divide that, I keep flip change. I'm only flipping the second fraction, and that's 2 pi times 2 is 4 pi. And that's why in that graph above, the red graph, the period was 4 pi. We could then find, that's a red graph. The blue graph, if we use the same formula, 2 pi over 1 because of that b value of 1, and that's why that period is just the typical 2 pi period. So here is our typical sine graph with a period of 2 pi, and that's because it has a b value of 1. Now note, as this b value gets larger, look what happens to that period. And so forth. This should remind you of a spring being compressed. Here we are back to its neutral point. Note what happens to the period as b becomes smaller. Notice how this period is longer. It should be reminding you of a spring that's being unwound. And notice, like, for example, this period is 10 pi. 0.2 b value is actually 1 over 5. So we're noticing that when we have these fractions where the numerator is 1 and the denominator gets larger, we get we get this wider effect. Of course, if b equals 0, we no longer have a sine graph. We just have a line. So it becomes a linear function. So we don't allow for a 0 to happen for the b value. Problem 2 is a good exercise in finding the periods graphically and without having to worry about all the details. So typically we'll find a period by picking a point and then seeing when it repeats again. So for example, I start at this point, I'm going through the graph, and I notice it repeats itself again at this point. That is a total distance of 8, and so the period is probably 8. What if you pick the wrong point, quote unquote? There is no wrong point. Okay? So for example, what if I pick this point right here? What if I pick a minimum instead? Then I go ahead and go from here, and I see when it repeats itself, and it repeats itself right here. Now, how do I find the period mathematically? We do the last point minus the first point. So, and we're not even talking about the points, we're just talking about the value on the x-axis. So this last point has an x value of 4 minus, and this first one had a value of negative 4. So that simplifies to 4 plus 4, which is 8. Interesting. So regardless of what point you pick, if we're doing this right, it should be the same period. So like, let's say, well, let's pick this one here for example, and it's going to repeat again right. Oh, where does this repeat? Right here. Okay, so we have a negative 2 x value, a 6 x value. So if we do 6 minus negative 2, we get 6 plus 2, which is the same period. Graph B, it's kind of a wider one, so it starts here and looks like it's going to repeat at this point right here. Started at a 0 x value, ended at a 12 x value. We subtract those two appropriately, we get a period of 12. Graph C.
I am the knight.
Batman.
I am Batman.
Okay, I got too excited there. So, let's pick a point. This is pretty fascinating. I'm gonna pick this ear right here. Okay, on Batman. So the right ear. At what point do I get to that same right ear on the Batman? But it's gotta be in the same position. So I travel all this and you're thinking, okay, well, there's an ear right here. Yeah, but it's inverted. I need to be the same ear point in the same position. So I'm looking like this right here. We're looking at a 2 minus a negative 4. And so the period is going to be 6. We showed you a few ways how to find the period of a sinusoidal graph. Take some time to summarize how to find the period from a graph itself.